All right. Problem set 2, Physics 214. What would you like to talk about? Number 1. Ooh, how my. Yo, Adrian, how creative. Number 1, nucleus of a nitrogen atom. Now, for this, we're not really interested in the whole it violates atomic properties. How dare you have a nitrogen nucleus just flying through the air with no electrons attached to it. Just to think of it as something with a mass of 7 times the mass of a proton plus 7 times the mass of a neutron. And proton mass, neutron mass, effectively it's the same thing. You can look that up on Wikipedia. It accelerates from rest at from one plate to another plate, and the potential difference is 10,000 volts. So it's 10,000 over here, 0 over there. Positive particles go from higher to lower potential, so that's how I draw this. What is its kinetic energy when it crosses the plates? What is its final velocity? If the distance between the plates is 20 millimeters, what's the E field magnitude, and what is the particle's acceleration? So here, initial velocity is 0. The potential energy is entirely dominated, well, the only source of energy at this point is the potential energy. The potential energy, just like that first problem in lab, is the charge times the delta V. So the potential energy is 7 times the charge of a proton times that 10,000. And that's the potential energy. Oop, let's get this fixed. So you can look all of that up. The potential energy, this particular value, is equal to 1/2 mv squared, where this m here is that m right there. So we're looking for the final velocity, so potential energy is equal to this 1/2 mv squared. So 2 potential energy divided by m is equal to v squared. Square root of 2 potential energy over m is equal to v. And then you solve for v. What is the if the distance is 0.22 millimeter, 20 millimeters, the E field magnitude, delta V, is equal to ED. So E is delta V, or 10,000, divided by 20 times 10 to the negative 3 meters. And that's the E field. In what direction, no, that's not it. What is the magnitude of the particle's acceleration? Well, QE is equal to MA. So QE over M is equal to A. Q is 7 times the charge of a proton. Mass is this. E field is what you get here. That's the acceleration. And that's problem 1. The kinetic energy is equal to, at this point, it is all potential energy. At the end, it's all kinetic energy. Since there's no friction, you could say that the potential energy initially is the kinetic energy at the final. Yeah, the initial energy is the same. Conservation, I would argue conservation of energy. There's no friction. So,
Underneath the square root there, we have potential energy.
yeah.
How do we calculate that number?
Well, it comes from this. Potential energy is the charge times the potential difference. Which is 7 times the charge of a proton. Okay, number 2. Proton, which means you know what the mass is and you know what the charge of the proton is heading directly at a nitrogen-14 nucleus. So the charge of this is 14 times the charge of a proton. So this is the charge moving at the nitrogen nucleus at a particular velocity, 5 times 10 to the 5th. The nucleus doesn't move. How close will the proton get to the nucleus before it comes to a stop? So what you're doing is you're looking at a particular distance x where the velocity at that point is 0.
So is the charge for this one the same as the charge for the one before?
Yes. This one is the same as this one. So this is a conservation of energy problem. The kinetic energy of this particle is being converted into potential energy by it being within proximity of the nucleus. So kinetic energy initial is potential energy final. Kinetic energy initial, 1/2 mass of the proton, velocity squared equals charge of the proton, potential energy at that point x. Now, the potential energy at that point x is kq of the nitrogen nucleus divided by the distance x. kq over r. But in this case, we're going to use x. So this gets changed into 1/2 mass of the proton, v squared equals charge of the proton, k charge of the nucleus divided by x. Solve for x. X equals 2 qp k qn over mp v squared. And that's it for 2.
The N is for
And the what? Excuse me?
the N, QN.
Q sub n is the charge of the nucleus.
Okay, that's right.
Charge of the nucleus is 7 times that of the proton.
So why did you put 14 times charge of the proton? Oh, yeah.
Why do I not put? Oh, because I'm an idiot. Because it's nitrogen nucleuses only have 7. Okay. So that's number 2. Number 3 is easy. And what I'll do is I'll just outline it and then you can handle it. You've got 3 charges, one at 3, 4, a positive charge, one at -2, 6. So you got a negative charge up here. I want to know the potential at that point. What you've got to do, you've got an R1 and an R2. So you've got to find those distances. Distance is simply, those R's are simply the delta X squared plus the delta Y squared square root. The V, the total V, is simply the potential of the positive one plus the potential of the negative one. Since you're dealing with a negative charge, this value here is going to be less than 0. So it's KQ1 over R1 plus KQ2 over R2, and Q2, since it's the negative charge, will be less than 0. All you have to do is add them together, and that's it. That's number 3. Number 4 is the kitten problem. In Lewis Hall, you have a completely surprised kitten. The kitten has a charge of -3 coulombs. So the charge is -3 coulombs. He is suspended in the air, doing nothing, completely unharmed. No wires are attached to the cute little thing. If the mass of the kitten is 5 kilograms, that's a big kitten. What is the magnitude of the E field? In what direction is the E field pointed? So here's the kitten. It has a force downward due to gravity of mg. So it must have a force related to the E field, which is Q times E, that should be pointed up. Since the kitten is a negative charged kitten, the direction of the E field must be down, because negative charged particles always feel forces in the opposite direction of the electric field. So the electric field force is down. The sum of the forces is equal to 0 because the kitten is not moving up or down, just sitting there. mg is down. QE is up. In this particular case, G and Q will both be magnitudes. These negatives or these signs determine if it's up or down. In this particular case, I don't let the negative signs hang out in the equations. They're shifty. They can't be trusted. So I like to keep them out where I can watch them. So mg is equal to QE. And E is mg over Q. M is 5, G is 10, Q is 3. So 50 divided by 3 is, I can't do basic math apparently, 16.67 newtons per coulomb.
Why is the Q not -3?
When you're summing up forces in the vertical, I like to deal with magnitudes. And if the force is pointing up, I know that force is positive because it's heading up. If I was going to do negative Q, then I would have to have another negative either out front or in front of the E, and I would be taking negatives of negatives. So I like to keep, when I sum forces, I like to keep my signs out front. The force from electricity is up, so it has to be positive. The force from gravity is down, so it has to be negative. And then I let those signs rule. Everything else deals with magnitude only.
So how do you know the direction of the E field for that one?
The negative charge always feels a force in the opposite direction of the E field. In order for the kitten not to be harmed, it has to be levitated. The force from the electric field must be pointed up. So if the force from the electric field is up, the electric field direction itself must be down because it's a negative charge.
Unless the force is up, because it said it'd be suspended in the air.
If the force wasn't up, it would fall.
Yeah.
So if the electric field was if the negative cat electric field pointed up, the force from the electric field would be down, the force of gravity would be down, and the cat would smack into the table. Unless it had a piece of buttered toast on the back, and then it would just sit there and spin forever.
Number 3, what was the R equals delta x squared? What do you have to use that for? Delta x squared
As
delta x squared.
for the first particle, it is at 3, 4. And you are at the potential of being measured is at 0, 0. So 3 and 4. So 3 squared, 4 squared, Pythagorean theorem. That you need the distance.
So what do you do with negative 2, 6? No.
2 squared plus 6 squared, square root. And that's the distance. Fortunately, I gave you the point to be measured at the origin. For that. This is where you're measuring it, that's where it is. In both cases, x naught and y naught are 0. If I'm here at 0, 0, and it's here at 3, 4, what's that length? X squared plus y squared,
Yeah, but
Pythagorean.
what are we looking for? Like, are we using?
You take that r and you put it in the potential, k q1 over r1.
Yeah, so you have to solve for R1 and R2. Correct?
Yeah. You get r1 and r2 and you plug those in.
Yeah.
Okay. Number 5, puppy power. Charge capsule of puppies to which the worst review I have ever received was very upset at the puppy power problem because I was putting puppies in harm's way. And I'm like, it is the student's responsibility to save the puppies. I did not put the puppies in motion. It doesn't say anything about me in this problem. Your job is to save the puppies. So let's do that. A charged capsule of puppies is flying from left to right through the region of space where the E field is 300 newtons per coulomb and is pointed in the direction of the velocity. So the velocity is to the right. The E field is to the right. It has a magnitude of 300 newtons per coulomb. The puppy capsule has a mass of 100 kilograms and is traveling at 50 meters per second. V is 50 meters per second. The mass is 100 kilograms. That's the total mass of puppies and capsule. The region of space is 1,000 meters long. So it starts over here. We could say the origin, the initial velocity is 50 meters per second. From beginning to end is 1,000 meters. At the end of this region is the wall of puppy death. What is the charge on the capsule so it reaches a complete stop at the wall? Please save the puppies. So we have to get the Q. Now really what we're going to deal with is the magnitude of the Q. If the E field is to the right and the velocity is to the right, to save the capsule of puppies, the acceleration must be to the left in order for this thing to slow down. If the E field is to the right and you need this electric force to be to the left because the acceleration is to the left, should the puppy capsule be positive or negative? In order for the acceleration to be to the left, it must feel an electric force to the left. The electric field itself is pointed to the right. Therefore, the charge on the puppy capsule should be negative. Correct. A negatively charged capsule will cause the force to be to the left, the acceleration to the left. It will slow down. Newton's first law, F equals ma. The force of a charge in an electric field is Q times E. I'm dumping signs. I only care about magnitude.
So how is the force to the left if it's falling to the right?
You can have acceleration opposite of velocity. If acceleration is opposite of velocity, it's slowing down. If acceleration is on the same side as velocity, it speeds up. We need this thing to slow down.
And the force and the acceleration is always the same.
Force and acceleration are always the same, yes.
So when you only care about magnitude, you see the direction then?
Well, yeah, really what's going to happen is that I'm going to apply the minus signs out front, and we'll see that. So really, the magnitude of acceleration is this, but when I substitute this in here, x naught is 0, v is 0, x is equal to v naught t minus 1/2 qe over m t squared. And then 0 equals v naught minus qe over mt. And that's where the minus signs are coming in. Right where I can see them. Now in this particular case, I don't know charge. I do. Oh no, this is going to be one of those. I don't know charge and I don't know time. But I do know final position, initial velocity, electric field, mass, V naught, mass, E. It's a 2-equation, 2 unknown. I have 2 equations, the position and velocity equation. Each one has 2 unknowns, time and charge of capsule. Now, in problem 5,
Why is the velocity 50? Oh, you're talking about the end.
the final velocity is 0, yes. In the problem, I don't make any mention of tell me how much time this thing takes. I don't ask for it. So what we do is we substitute it out. We eliminate it. To eliminate it, bring that over there, QE over MT is equal to V naught. So time is equal to V naught M over QE. And I take this and I plug it in here. X V naught M over QE for the first t minus 1/2 QE over M t squared V naught squared M squared Q squared E squared. Over here, I'm going to simplify it. Just bring the V naught in. V naught squared M over QE. There's an M here and an M squared there. That cancels. There's a QE here and a Q squared E squared there. They cancel. Over here, I've got this minus V naught squared M over QE. And there is a 2. Factor out a V naught squared M over QE. All that's left is a 1 and a minus 1/2. So this collapsed. 1 minus 1/2 is 1/2. I'm left with V naught squared M over 2 QE.
So why couldn't you cancel the V naught, whenever you cancel it?
Well, what's the real question? Hold on. Say your question again.
Like, whenever you cancel like the M's and all that on the first step, why didn't you cancel the V naught?
Because I need to keep V naught in there. I can't cancel out V naught. That's a necessary variable. And we know what X is, so all I got to do now is Q equals V naught squared M over 2X E. Now, one of the interesting things that you can see is, or ask yourself is, it's a lot of variables, a lot of letters. Are we sure we're right? Well, let's take a look at it. V naught is a velocity, meters per second, or meters squared, second squared. M is the mass, kilograms. X is a distance, M. E, electric fields are measured in newtons per coulomb. One of the meters cancels with that. We have meter per second squared times kilogram. That is a newton. Newtons cancels. Coulomb, which is in the denominator of the denominator, pops up. Coulombs is numerators units. Problem solved. So that's the expression. Plug it in, use the number. Just remember, this particular Q is magnitude. So when the answer is, what's the charge on the capsule, you just say negative of this. We know from the setup of the problem that the charge of the capsule should be negative. What this did here was it determined the charge, magnitude. So if we know that, let's say that's 2 coulombs. We know that the charge should be negative, and we got a magnitude of 2. The answer is negative 2 coulombs.
Would it also drive less than negative out, said 2 coulombs to the left? Or,
No, well, no. charge is a scalar, it has no direction? Good question, though. It caused a brief revolution in my brain for about half a second. All right, number 6 is like number 5. So what I'm going to do is I'm going to skip it, but it uses the same equations that you would use for number 5, or that you do use for number 5. But in the case of number 5, you didn't know time. In the case of 6, now you do. In the case of 5, you didn't know the charge. In 6, now you do. In number 5, you knew where it stopped. Number 6, you don't know where it stops. So really, it's the same equation, same setup as this. It's just that instead of not knowing position and not knowing time, you now know those things, and there are a couple other unknowns. It's the same thing. The setup's the same. Now, in the question, would it stop in the same place if it was a negative charge? Why or why not? In problem 6, the E field is to the left. And it's a positive charge that's moving to the right. It comes to a stop because positive charge feels force in the same direction as the E field, and so eventually it stops. In the second part of 6, if it was a negative charge moving to the right, in an E field that's headed to the left, it would feel a force to the right and accelerate. Would it stop in the same place if it was a negative charge? Not only would it not stop in the same place, it wouldn't stop at all. It would just accelerate out to infinity. What I'm going to do now is talk about circuits. What you guys need to know is I'm only going to do number 8 and 10 because 7, 8, and 9 are the same problem, effectively. It's lather, rinse, repeat. There's no sense in doing all 3 versions. What I'll do is I'll post the videos from the tutorial for last time I taught 214 last summer, and you guys can look at that and figure it out. It may be that I did 7 and 9 back then, I don't know. But at least it goes over the skills that you need. For number 8,
Just a general question.
yes.
Does the shape of it matter, like rounded corners versus?
No. And that is one of the things that that my TAs, when I was a student, said, what's the difference between the 3 circuits? Answer, nothing. The shape has nothing to do with it. The relationship of the resistors with each other does. a lot of times the student, this is what the TAs told me, you're going to look at that and freak out. How dare it be shaped this way? I'm only used to doing things this way. Ooh, scary. And what did we do? We freaked out. So what I'm doing with you guys is I'm showing you that this is exactly the same thing, and a percentage of you will still go, I'm freaking out. It's all at a weird angle. If you could take the wires and bend it, you can bend it in any direction, paying attention to do two things. Don't move nodes past resistors. Don't physically rip the wire apart and plug it into something else. Otherwise, it'll change. So for number 8, 8 is a standard circuit problem. With all circuit problems, solve REQ first. Get that first. We will squoosh the circuit.
Can we write the relationships before we start? Is that
Define relationship.
like 1 over R,
Oh,
like that?
so there are two main relationships, parallel if you can draw a box around two resistors where one line goes in and only one line goes out, you can change it using this. You could have a situation where there are parallel resistors. Once again, I can draw a little box around the whole thing, one wire in, one wire out. And these are not parallel, they're series. It is 3 o'clock on a Friday afternoon. I barely know who I am. These are parallel. To get parallel equivalent resistance, it's REQ 1 over R1 plus 1 over R2 inverted. Now, sometimes people write it like this, R1 minus 1 plus R2 minus 1, like that. It could be expressed in any of those ways. So what we're going to do is we're going to squish this circuit down using multiple equivalent resistances step by step until we get one resistor. Drawing just the resistors Okay. And notice I'm not using numbers yet. What we're going to do is we're going to draw boxes. The box that I first draw is around 4 and 5. Because I can draw a box around 4 and 5, one wire in, one wire out. There are no splits. It is one parallel resistor. Or one set of parallel resistors. If I circled R2, 4, and 5, I've got R2 in series with a parallel R4 and 5. I can't do that just yet. This swooshes down R4, 5. and R6. The next box for squooshing is this. R245. The next box I draw is this. So in each of these boxes, there is either one set of series resistors or one set of parallel resistors. The order number really doesn't matter. It's just, I'm just keeping track of stuff. And then you draw a box around the whole thing. These are 3 series resistors with each other. And then the last one is REQ. So those are the steps that we use in order to get R equivalent. R45 is the equivalent resistance of an R4 and an R5 in parallel. 1 over R4 plus 1 over R5 inverted. The first thing we do really is outline what we need to do, and then we start working the math. R4, 30. R5, 10. So R45 is 7.5 ohms. Now, R245 is a series resistor. R2 plus R45. R2 is 12. R45 is 7.5. So this is 19.5 ohms. And that is R245. R2345 is 1 over R3 plus 1 over R245 inverted, which is equal to 1 over R3, which is 9. Oh, whoa, stop. I was picking units off the wrong one. R4 is 10. R5 is 15. Glad I caught this. Which makes this 6. R45 is 6 instead of 7.5, so this becomes 18. R2345, R3 is 9. R245 is 18. Which gives me 6 ohms again. Trying to see, I'm double checking everything. 10 and 15 in parallel. That gives me 6. 6 plus R2, R2 is 12, that's 18. R3 is 9, 1 over 9 plus 1 over 18. Inverted is 6. All right, so R2345 is 6. And then R equivalent is R1 plus R2, 3, 4, 5 plus R6. R1 is 6, R2, 3, 4, 5 is 6, and R6 is 25. So 37 ohms is the equivalent resistance of the circuit. That's what you do at the very beginning. Doesn't matter what I ask for, what you need to know immediately is what is REQ. The next thing you always need to find out is what is the current total running through the circuit, the current running through the battery. I naught is REQ over, V of the battery over REQ. V of the battery is 5, REQ is 37. So the total current it's 5/37. We need that information, or 0.135 repeating amps. Now really what I'm doing is I'm looking for everything. I'm looking for all the currents flowing through each of the resistors. I'm looking for the points here, here, and there. And really what I want to do now is draw this circuit a lot larger, just so that we can see what's going on.
Get R1 and R6.
Hold on just a second.
It's ridiculous.
What was your question?
How do you get R1 and R6? Can you do R equivalent?
When I get R1 and R6, well, R1 and R6 are given on the problem. 3 resistors are in this last smooshing. You have 3 resistors in series. 3 resistors in series, you just add them up. R1, R2, 3, 4, 5, R6. Bam, bam, bam. Put them together.
So R2, 3, 4, 5 isn't the same as adding all of the.
Oh no, because those are all in parallel, and some are in, some of the sub pieces are in series. It's not a pretty thing. If you have 3 resistors in series, 4 resistors in series, 5 resistors in series, 1,000 resistors in series, you just add them up. For parallel, it's 1 over the first one plus 1 over the second one plus 1 over the third. They have to all be in series or all in parallel. They cannot be a combination of both when you smoosh. The points that interest me on this are A, B, C, and D. Let's knock out some easy stuff. The potential, if it's connected by wire and does not pass through a battery or a resistor, all have the same potential. They're all connected to ground. So they all have a potential of 0 volts. Above the battery, you go from 0 across a 5-volt battery, from the small end to the big end, which means this entire end, including VA, is 5 volts. Now, this is going to be a piece of paper we're going to keep track of. It's like our Sudoku puzzle. We need to be able to identify areas where we know everything about Ohm's law. The current, its magnitude, is potential high minus potential low divided by resistance. If we know 3 of those 4 things for any resistor, we can identify the 4th. Such as I1 going across R1, on the high end we have VA, on the low end we have VB. I1 is the current flowing through the R1 resistor. What is the difference between I0 and I1? Nothing. The current doesn't split. So I0 is equal to I1. That means we know the current flowing through R1, we know R1 itself, we know VA or the high, so IR equals to V high minus V low, so V low is equal to V high minus IR. V high is 5, I is 5/37, R1 is 6. So the potential at B, which is the low point, and the fractions are going to get a little bit messy. 155 over 37, or 4.189 repeat. The 189 repeats. When I get to the test, what I try to do is set up common factors so that you're not going to get these obscene, weird fractions. I'm going to try to keep everything in the like 1/3, 2/3, 5/4, stuff like that. So now I know V sub B. I now know the potential at this point. I know what I1 is. And now I've gotten to a point where I'm not really sure how to go, because across R2, I'm not certain about the current flowing through R2 or the current flowing through R3, and I don't know the low potential on either end of R2 or R3, so I gotta kind of stop on this end. What I do is I'm gonna work backwards across R6. R6, the current flowing through R6 is V sub D minus 0 divided by R6. The current flowing through R6 starts here, ends here, and it ends at ground. The high will be V sub D. The low is 0. The resistance is R6. I know what I6 is. I6 is I0 because the current flowing from R6 does not split when heading to the battery. So I6 must be I0. So V sub D is I6 R6, which is 5/37 times R6, which is 25. And I think it would probably just be 125/37. Leave it to me to pick just a freakish fraction. But numerically, V sub D is 3.378 repeat volt. And I now know V sub D. And if I know V sub D, look at what's known and unknown. R2 I can't really work with because I don't know the current flowing through R2 and I don't know V sub C yet. But across R3, I know the high potential 4.189. I know the low potential 3.378. And I know the resistor R3. From that, I can determine I3. The VB 155.37, the VD 125.37 over R3, which is 9. So it's 30/37 divided by 9. Which is either 0.0900 repeat or 10/111 amp. And that is the current going through I3.
Do you want, answers given as?
When I ask for an answer, it is in the form, it is decimal. When you work with the problem, keep it in fractions. Otherwise, you're dumping information and it gets bad. Now, this is where we take a little bit of a different approach. Granted, I do not know the current flowing through R2, and I do not know the potential at C. So I can't really use Ohm's law to do this. However, if you look at the node B, you know that I0 or I1 comes into the node. And you know that I3 and I2 come out. So the current flowing into B is equal to the sum of the currents flowing out, like a stream forking. I0 is equal to I2 plus I3. Or I2 is equal to I0 minus I3. So I3 is 10/111. I0 is 5/37. And I'm left with 5,111, or 0.045 repeat amp. And that is the current flowing through R2. So it's like you just got to find the weak part in the problem and just start peeling it back. With the resistor R2, I know the high, I know the resistance, I now know the current, I can get C. C is now allowed, the low. VB minus VC over R2 is equal to I2. Solve for VC. VB minus VC is equal to I2 R2. VB minus I2 R2 is equal to VC. And this really, what I should be doing is what I would recommend, take all of these values at the very beginning, make a chart. So rather than having to hunt down these numbers, as you discover them, write them down so that you can easily refer to them again. VB, 155 over 37. I2, excuse me? 5 over 111, thank you. R2 is 12. So VC .65 volts, or 135 over 37 volts. And that is now VC. Okay.
Could we just highlight the steps to find, like, we'll get through to get C?
Okay. You mean from the very start?
No, just, we found the first half, we found B, and then we went back and we found
Mm-hmm.
D.
Um,
And then we worked from what pieces we needed to find. And then we get-
so we found V sub D, and then once V sub D was found, we find I3, and once we have I3, we find I2, and then once we find I2, we find VC. And now that we have V sub C, we find I4 and I5, and then we're done. Because we found everything. Like with a Sudoku puzzle, you just don't wander out into the area of the square where you know nothing about. You look for the one thing where you know 3 of the 4 quantities: the high potential, low potential, resistance, and current. If you know 3 of those 4, whether it's at the beginning of the problem or at the end, you attack that first. I4 and I5, you could do either one. Why? Because we know the high, the low, and the resistance in both cases. I4, VC minus VD over R4. I5, VC minus VD over R5. VC 135 over 37 minus 125 over 37 divided by R4, which is 10. Same thing here, 135 over 37, 125 over 37, R5, 15. In both cases, 10 divided by 37 is the numerator. .027 repeat.
High always on the left and the low on the right.
Yeah, that's how I usually do it. I just say high and low because I'm only interested in the magnitude of the current and I know where it goes. 0.018 repeat, or 2 over 111 is I5 and I6. And the interesting thing is, if you take I4, which is 1/37, I5, which is 2 1/11, and you take I3, which is 10 1/11, you get 5/37, which is I0. The current flowing through this, that, and that, at that particular point, all eventually end up back into being I0. So at this particular case, I4 and 5 and I3 should add up to I0. For this case, I2 and I3 should add up to I0. The currents should be conserved. And this is why you use fractions, because fractions do not round and you will get exact answers. And that's problem 8. So you do the same thing for 7 and 9.
You sure you want us to do number 7 and 9?
I require you to do 7 and 9, because what else do you do on a Sunday afternoon? Physics. So you're shaking your head no. All right. So that's the problem. The reason why it took so long is that we did it slowly. We answered questions. We explored the space. Once you figure out what you're doing, stuff like this should get knocked out fairly quickly.
Okay, which one did you say, some to I0? All of them?
All of them should, no, 4, 5, and 3 should add up to be I0, which is 5/37, and it does.
How come I2 not included in that?
Because I2 is I4 and 5 together. If you look up the number for I2, add it to I3, you'll get I0. It just adds up because current is conserved. And just so we know, next week, we are not going this late. 4 o'clock is the beginning of the baseball season, so we're getting out early. I may end up posting the videos from last year and just letting you guys look at that rather than do this live. Last problem. Now really, 10 is the same thing, a little more on the easy side. Now, would I give you a problem as complex as this on the test? No. Serious about this, no. Something a little more watered down. I'll try to get it posted today. Last week, what I found is YouTube takes a little bit of time to process 2 3 gigabyte video files just to upload it, process it, and get it ready. So if it's not up tonight, it will be ready by tomorrow morning. Number 10, all the resistors are identical. I give you the potential difference of the battery and the current. So I naught is 0.5 and V naught is 20. I want the value of R. So what we're doing is we're kind of doing things in reverse, where I give you the current and now we're looking for resistors rather than given the resistors, find the current.
It's not 500. I know it's
500 milliamps. So we've got R, all of them are R. The middle resistor changes to something a little bit more conventional. Like this. The first box that I smoosh is this. 3 resistors all in parallel. This box I'll call RA. Oh, and the other thing that I'm going to do is smush that box. That's RB. You develop an instinct on how to attack it. You just start looking for where you can put boxes. When I see this, I can box this, where I get 2 series resistors all in the same thing. Here I can draw another box, 3 resistors all series. You just start looking at it and you can see patterns. The next box is this. And then R equivalent.
Does it matter which box you do first?
No, you can do that one or that one, either one. So RA is 3 R resistors all in parallel. So RA is equal to 1 over R plus 1 over R plus 1 over R inverted. That is 3 over R inverted, or R over 3. So RA has a value of R over 3. RB is 2 resistors in series, R plus R. So RB is 2R. So we've done this. Now to go from there to here, I've got to take RB and another R resistor in parallel to form RC. So RC is 1 over RB plus 1 over R inverted. RB is 2R, so 1 over 2R plus 1 over R is this. Common factor is 2R, so it is 1 over 2R plus 2 over 2R inverted. 1 plus 2 is 3, 3 over 2R inverted. 2R over 3 is RC. The last part, RA, RC, and R all lined up to be REQ, excuse me. So REQ is R plus RC plus RA. 1 plus 2/3 plus 1/3 is 2. So REQ is 2R. So the equivalent resistance is 2 times the value of the resistor. Not always, it depends on the arrangement of the resistors. Now we use Ohm's law. I is V over R EQ. So I is V over 2R, or R is V over 2I. V is 20. 2 times I is 0.5. 2 times 1/2 is 1. So R is 20 ohms. Done. So it's just getting into practice using series and parallel circuits and Ohm's law. Bang, bang, bang.
Where'd you get from 1 over 2R plus 1 over R to 1 over 2R plus 2 over 2R?
You mean this? When you're adding 1 over 2R and 1 over R, the common factor has to, or the common denominator has to be 2R. So this 1 over R becomes 2 over 2R. And now 1 plus 2, or 3 over 2R. And then there you go. All right, that's it. I'm done. I'm going home after I post this. See you guys later.